Hello, Calc students. So we are going to be looking at finding volumes of solids of revolution. And you did this last year. We did it at the end of AB last year, kind of right before the school closure. So we're going to review that today. And then we're also going to look at the shell method that we didn't talk about. So we did disk and washer last year, and we're also going to do shell. So the shell method is not on the AP exam. However, it's a handy thing to have in your back pocket in case you come up to something you're trying to integrate and it's really hard to either change the limits of integration or integrate with respect to y instead of x. And so the shell method kind of comes in handy for the in place of the washer method when that comes up. So I'm going to go ahead and share my screen and start the presentation. So I'm going to start the slideshow. So this first slide is a warm-up. You actually did this warm-up last year. If you'd like to pause the video and go ahead and give it a try and review it, you may. And then we're just going to go ahead on to the next slide. This is a little area between two curves practice. So kind of like what you were doing in the assignment on Monday with the shark problem. So go ahead and pause it, give it a try, and we'll come back. All right, welcome back. We're going to continue with our slide presentation, and we're going to review the disk method. And the disk method, remember, relies on us using, that the area of a circle is pi r squared. So if you think of a disk is kind of like, M&M shaped. You start with some curve, and if you rotate that, it turns into a circular shape or a disk. And since we know the area of a circle or a circular shape is pi r squared, we essentially use that same idea when we have the disk method. And so this first question says, find the volume of a solid formed by revolving the region bounded by the graph of y equals 4 minus x squared and the x-axis from 0 to 2 about the x-axis. So I think it's helpful to draw a little sketch. It doesn't have to be too elaborate. So I have the curve 4 minus x squared. So I know it goes through 4. It's concave down. I can find that it intersects the x-axis at 2 and negative 2. So my curve goes this way. Oop, missed that there a little bit. And in this question, you're actually asked to find the area under the curve bounded by the graph and the x-axis from 0 to 2. So we're trying to find the area of this shaded region here. All right, we talk about when we're doing these problems that we have what we call a representative rectangle that we're rotating. So if I have some rectangle here that's in this region, so the rectangle has essentially a two-dimensional shape, but when I revolve it around this x-axis, it's going to spin out the shape of a circle, and that's where we get the form of our integral. So we're going to have pi times the integral from 0 to 2. Our radius then, the radius of this shape, this circle that we're spinning, the radius is just the height of this curve. So it's 4 minus x squared. And it's times the radius squared dx. So again, all of this comes from the fact that the area of a circle is pi times radius squared. So if we are revolving and our axis of revolution covers one side of the shape we're trying to rotate, it is a disk. So it's pi times the integral of the radius squared. And we think of this as being a big R here. So then we simplify that. So we have the integral from 0 to 2. If I square this, I have 16 minus 8x squared plus x to the 4th. Again, x to the 4th dx. And that is a 0 there. It's hard to tell. All right, so we're going to go and find the antiderivative. So I keep my pi. Antiderivative of 16 is 16x. Antiderivative of negative 8x squared is negative 8/3 x cubed. Plus x to the 4th. Antiderivative is 1/5 x to the 5th. Right. Then we're evaluating that from 0 to 2. So I plug in 2, and that's going to give me 32 minus 2 cubed is 8. 8 times 8 is 64/3 plus 2 to the 5th is 32/5. And then if I simplify that, I'll grab my calculator here. We have 32 minus 64/3 plus 32/5. And that is 256/15 times pi. Okay. And that's the area of that region. All right, let's look at another example. Okay, this time we have a solid formed by revolving the region bound by f of x equals 2x squared and g of x, and we're revolving around the line y equals 8. All right, so let's look at what we have this time. So we have a parabola again, 2x squared. And then we have the line y equals 8. All right, so it's this region in here. Sorry, it's kind of crooked. And so we're trying to find this. So in order to set up our limits of integration, we need to know where these points of intersection are between these two curves. So I take my 2x squared and set it equal to 8 because I want to know what those x values are. So I divide both sides by 2, I get x squared equals 4. And so those points of intersection are at plus or minus 2. All right, so I set up my integral. I have my pi. I know that the integral is going from -2 to 2. But what we need to notice this time is that our axis of revolution isn't the x-axis. This time our axis of revolution is this line. So I'm taking my representative rectangle and I'm revolving it around this line. All right, so one thing I like to think of is this rectangle here is the difference between the curves y equals 8 and the curve y equals 2x squared. So it's the difference between those two things that I'm going to be squaring from my radius. So my radius is, and I can either think of it as 8 minus 2x squared or 2x squared minus 8. Either way, we're going to be squaring that. Right, so if I look at this and I have, well, the distance from here to here is 8. The distance from here to here is my 2x squared. And so this representative rectangle is the difference between those two curves. So 8 minus 2x squared dx. All right, one thing to notice about this graph too is it is symmetric about the y-axis. So if I want to save myself a little work on my evaluating end, instead of making this pi times the integral from -2 to 2, I can rewrite it as 2 times pi times the integral from 0 to 2. Then I'm going to go ahead and do these calculations inside here. That would be 64 minus 32 x squared plus 4x to the 4th dx. And again, I can simplify some more. looks like everything here is divisible by 4. So I'm going to take a 4 outside the integral. So that's going to give me 8 pi times the integral from 0 to 2. And remember, we're dividing everything by 4. So that turns this into 16 minus 8x squared plus x to the 4th dx. All right, at this point, we are going to be finding the antiderivative. So we have 8 pi that we still need to remember to multiply in at the end. Antiderivative of 16 is 16x. Antiderivative of negative 8x squared is negative 8/3 x cubed. And the antiderivative of x to the 4th is 1/5 x to the 5th. And we are evaluating that from 0 to 2. That's a 0. All right, so do some simplifying. We have 8 pi inside here. And remember our 0 term, when we go to subtract that, that's going to go away because each one of these has an x, so I don't need to worry about 0. So I'm just going to do the 2. 16 times 2 is 32. Here we have 2 cubed is 8 times 8 is 64 thirds. Sorry, my pen is not cooperating. Plus 2 to the 5th is 32 fifths. And so we get a solution of, got 32 minus 64 thirds plus 32 fifths. So we have 8 pi. Actually, I'm going to make this look like an arrow here. 8 pi, whoa, times 256 fifteenths, which is going to give us 2,048 fifteenths pi. Right, and that's the area under the curve. All right, let's look at the next slide. All right, this time we have find the volume of the solid formed by revolving the region from 0 to pi over 4, bounded by the y-axis, and the graphs of cosine x and sine x. So again, I'm going to draw a little sketch. I'd like to see what this looks like. And I don't need too much of the graph because we're only going from 0 to pi over 4. So I'm going to put in here, I'll go ahead and put my pi over 4. I'll put pi over 2. All right, just to get an idea of what it looks like. So I'm going to start with the sine curve. So the sine of 0 is 0. The sine of pi over 2 is 1. And in here we have square root of 2 over 2 in there somewhere. So here's my sine curve. All right, I'm going to switch colors here. So cosine starts at 1 and at pi over 2 is 0. So the cosine curve is coming in here. Right, so this is where they're meeting. This is our square root of 2 over 2, this point of intersection. And so it's asking us to find, I'm going to change colors again here. It's asking us to find the volume of the solid formed by revolving the region from 0 to pi over 4, bounded by the y-axis and these two graphs. So it's this region in here that I'm trying to find the volume of. And we're revolving around, I think we're revolving around the x-axis, and I don't think it says that there. But this is what we're doing in this problem. Switch it up again here. We are taking one of these representative rectangles, and we're going to revolve it all the way around the x-axis down here. And so this is one of our washer problems where we have this gap between the curves and the axis of revolution. So unlike the disk, where a disk contains one side of whatever the region is, there's a gap here between it. And so I'm going to look at my big radius, which is this distance here. So my big radius is the cosine curve. My little radius is this distance, which is the sine curve. And so to find the volume of that solid when we revolve it, we still have pi, but we're going to have the integral from 0 to pi over 4 of the big radius squared, which looks like cosine, right? That's the blue one, the one on top. So cosine of x squared, that's our big R, minus, now we have to do the little radius, which in this case is sine squared dx. All right, so another way to rewrite that is the integral from 0 to pi over 4. This does not like to draw zeros. There we go. Cosine of x squared is the same thing as cosine squared x. Minus, and this turns into sine squared x. And hopefully this looks familiar to you. This is a trig identity. It happens to be, put a note in here, this is actually the double angle identity and I don't know why this pen has decided to stop working again. It is the double angle identity. Oof. Let's see if we can get it right. For cosine. All right, so maybe you can't read what that says, but I'll just tell you it's the double angle identity for cosine. And so I can rewrite that integral as the integral from, let's see if I can get this pen back on track here, 0 to pi over 4 of, and this turns into cosine 2x dx. And it's really nice to notice that it's a double angle identity. It makes it a lot easier for the integration process. So at this point, I'd be asking myself, well, was the chain rule done correctly? Well, if I end up with something that looks like cosine 2x, there should have been a 2 in here. And so if I put the 2 in, I need to take a 1/2 outside. So this turns into pi over 2 out here. And I'm going to go and find the antiderivative of cosine 2x. So if I have cosine, it should have been a sine of 2x. And we're evaluating that from 0 to pi over 4. All right, so I'm going to go ahead and do that. So when I plug in pi over 4, I have 2 times pi over 4, which is pi over 2, and the sine of pi over 2 is 1. So this is pi over 2 times 1 minus, and when I plug in 0, 2 times 0 is 0, the sine of 0 is 0. So I have 1 minus 0, and so I just end up with the area between those two curves is pi over 2. All right, this next one says set up but do not solve each of the following. So this time, and this comes up a lot, I've seen this many times on the AP exam, where this will be in a free response section, where all they want you to do is set up the integral. So they want you to know, oh, it's a washer, here's what it would look like, but they don't ask you to actually solve it all the way. So it says find the volume of the solid that results when the area of the regions bounded by y equals x squared. So I'm going to get a little idea of what that looks like. And then we have the line y equals 4x, so it has a y-intercept of 0 and a slope of up 4 over 1. So that's coming in here somewhere, so it's this region. And we are revolving it around the line y equals -2. And so there is going to be this gap here. So this is our axis of revolution. And I'm taking my representative rectangle. I'm going to switch colors here. I'm taking a representative rectangle and I'm revolving it around this, right? So we have a horizontal axis of revolution. Our representative rectangle is perpendicular to that. And so this is a classic washer problem. So we need to notice that this distance here from this line all the way down to here, our big radius in this case, I'm going to set it up. I have pi times, and I need to find out my limits of integration. So my big R here is this distance from this line all the way down to -2. So that's the line 4x. And I can think of that as minus a -2, right? That's how far I'm going, or 4x plus 2 squared, that's my big R, minus, and this time the little rectangle is this, or excuse me, the little r is this distance here from the curve down to that line. That's my little r, that's my big R. And so my little r is the x squared minus the -2. And that is also squared dx. And they are going to look to see, do you know what the limits of integration are? So I need to find out, where does this curve intersect this line? So I have over here, where is x squared equal to 4x? I'm going to move the 4x over, and you can probably tell from the graph where these points of intersection are, but I'm going to go ahead and find them. These have an x in common. So I have x times the quantity x minus 4. And so my limits of integration are 0 for this first point, and this other point of intersection is 4. And you could leave it right like that, or you could do a little simplifying in here. And I could make this 4x plus 2 quantity squared minus x squared plus 2 quantity squared. And then I'm taking that all with respect to x. They don't ask you to go any further than that. You could even leave this here like this. It wouldn't matter if these were switched and you had 2 minus 4x, because when you're squaring it, it's going to make up for that, whether you have this listed first or that. And that's as far as you have to go. All right, on number 5, it says find the volume of the solid that results when the area bounded by y equals x squared and y equals 4x is revolved about the line x equals -2. So this time we have the same shape that we're revolving. So we have x squared again. We have our line. It's this area again, only this time we have a vertical axis of revolution, because we're going around the line x equals -2 out here. So my representative rectangle is this direction, and I'm revolving it all the way around here. And so this time I am going to need to rewrite each of these equations in terms of x equals. So this first equation is going to turn into x equals the square root of y. The second one turns into x equals y over 4, or 1/4 y. Right? Again, we need to know these points of intersection. So we know this one is 0. And so when it was this direction, our upper limit was 4, but now we need to look at what the y values are. So when x is 4, y is 16. So this time, our limits of integration are going from 0 to 16. Our big R this time is this distance all the way from this curve to that x equals -2. And so we have for our big R, we have, and that's the one that's the square root of y. So we have the square root of y minus a -2 squared. All right, that's big R minus our other one is our 1/4 y minus a -2 squared. That's a y, by the way. Right, and again, we could clean that up and rewrite it as 0 to 16 square root of y plus 2 squared. Oh, that's a 2, doesn't look like it. Minus, wow, minus 1/4 y. Sorry about the pen. Plus 2 squared. And I lost track of whether I was using brackets or parentheses here, so that's a little confusing looking. And then this time it is respect to y, and I should have had a dy in here as well. All right, our last one on here, our last slide this time is talking about the, this would be a reason we would want to use the shell method. And so the shell method is you have your axis of revolution is parallel to one of your representative rectangles. It's actually kind of nice because then you don't have to rewrite things. So we have the line, or excuse me, the curve y, oops, go back. Let's get a pen. We have y equals 1/2 x squared That's supposed to be a curve there. Mine kind of looks like an absolute value. And we are going on the x-axis from 0 to 6. I'm just going to make a 6 here. And we're bound by the x-axis, y equals 0. So it is this region. This is the region we have here. And we are revolving this around the y-axis. I'm going to change colors here for a second. So our representative rectangle is here. Let's see, let's go this way. And we're revolving around the y-axis. Okay, so our representative rectangle is parallel to our axis of revolution this time. So we set it up, and it's kind of like, if you remember, when you unwrap a cylinder, when you're trying to find the surface area of a cylinder, and you have that 2 pi, right? When you unwrap that edge of the circle, it's the same idea with the shell method. You're dealing with a cylinder. So we have 2 pi on the outside. Our integral goes from here, 0 to 6, so we keep it in terms of x here. You have to put in what your like average radius is here. And so if I go from here over to whatever this representative rectangle is, that's a distance of x. And then we have that times the average, height of one of our rectangles would be this distance up to the curve. So times 1/2 x squared. And so notice this time we don't have to square anything, which is nice as well. No reason to get confused there. So it's like 2 pi, the radius times the height in there. So I'm going to simplify that. So I have 2 pi times the integral from 0 to 6. This turns into 1/2 x cubed dx. I can bring that 1/2 outside before integrating. So I have 1/2 times the integral from 0 to 6 of x cubed dx. At this point, I'm ready to find the antiderivative. So it's pi times 1/4 x to the 4th you're going from 0 to 6. So I have 6 to the 4th divided by 4. So let's do that. So 6 to the 4th divided by 4 is 324. I could subtract 0. When I plug 0 in, I get a 0. So we end up with 324 pi. One thing you might want to do just to check that the shell method works is to redo this problem. And I have it on the notes if you look online. You can do a little check by using the washer method. That says check, check with washer. So if you are using the washer method with this, you will have to rewrite this, right, in terms of x equals. And you'll also need to change your limits of integration. So if you look at the notes online, you'll see that I've worked this out. And you can either use the washer method and rewrite this and change your limits of integration, or you can see that the shell method also works. All right, that's our last slide on this. Your assignment is a circuit worksheet. You'll have 2 class periods to do this. These notes I realize were really long. So good luck, and just let me know if you have any questions. Good luck.